Hello, my name is Javier Brooks, and along with my teammates Jordan Feigelman and Javier Diaz, we'll be presenting to you our NASA competition mining robot. In this competition, we are trying to create a mining robot that can operate and collect surface materials such as dirt, rocks, simulating conditions on the surface of Mars. Our motivations are to work in conjunction with universities across the globe in order to aid NASA in its ongoing work of space exploration and eventual colonization. Now, our goals are to fully design a robot from top to bottom with every system required in order to perform the task that is assigned to us by this competition. Our secondary goals is to utilize as much resources and components as we can from FIU's Robotics Club. The task provided to us is to have our mining robot travel a set distance to a certain location, and then from there begin excavation of a regolith-like material known as Black Point 1, which is designed to simulate the surface of Mars. And then after it's excavated this material, to store it in its collection bin, travel back with it to a specified dump site, and then dispense its payload. This competition requires us to keep in mind the mass of the robot, the mass of material which is being collected, the total bandwidth which we are utilizing in the operation of our robot, as well as the dust and the design's tolerance for mechanical failure. It needs to be able to operate within these dimensions before being fully deployed, where it can expand to double those dimensions. The competition area, as seen here, has a slight grade, which we will be taking into account in the design of our robot, as well as, more importantly, the 0.55 meters above the regolith surface, which is the height that our robot needs to be able to dispense its payload from. This is important because the regolith surface is variable, so it needs to account for that.
Hello, I'm Javier Diaz, and I'll be telling you about the different designs that we considered for the scooping component of our robot. First of all, we're going to begin with the scooper mounted on an arm, which can be a very frontal-heavy system, and it usually requires the structure of the robot to either be anchored down onto the ground or to have counterweight. And because one of our design goals is to minimize weight, we decided not to use this system. Next up, we have a rotating drum, which is also frontal-heavy, and the material that's excavated is stored inside the cylinder. And there is no easy and inexpensive way of getting that material out and up into the clearance height that is required for the competition. So for that reason, we decided not to use the system. Over here, we have a system of a belt fitted with scoopers, and it's complex and has a lot of moving parts. And the dust, the material that's being collected can let dust fall back onto these pieces, and then that can negatively affect our score in the competition. As well as there's the chance that one of the individual scoopers may encounter a rock inside the regolith material, and that can damage the scooper or it can jeopardize the entire belt. So we consider this to be a system with a high chance of mechanical failure. For that reason, we're not going to use it. So that leaves us with the frontal scooper with actuators, which is simple and easy to manufacture. And one of its downsides is that it requires a lot of user input, and we plan to address that with automation. Next up, we'll be looking at our options for the drivetrain, and it's between wheels and treads. And the wheels have a low surface area contact with the ground, and the material that we're dealing with has a very fine grain. It's almost like a powder, and we expect that wheels will probably sink into the ground and spin in place. So because of that, we concluded that treads are superior for covering this type of variable terrain.
Good afternoon. So I'm here to discuss with you guys a few of our design considerations and alternatives. Initially, we had decided to use wheels. As my partner Javier previously stated, wheels have a low surface contact with the ground, and from our previous image, you can see it would dig into the ground. Our initial suspension setup was that of an UTV. It has a rear-mounted swing arm with a centrally located suspension. 2 control arms in the front with individual suspension. This system would require a rack and pinion setup, which has a lot of moving parts and has a high chance of mechanical failure. So furthermore, we moved on to our tank tread application here. Our first design had what's called a horizontal suspension setup. Now, as you can see in the image here, there is no way to stop the suspension from really bottoming out. This could cause the tank treads to pop off the tracks and also has a high chance of mechanical failure. So to complement this, we decided to go with this final design here. It contains a perpendicular suspension with a bump stop. This allows the suspension to bottom out, take all the forces and reduce shock on the framing components without having the treads pop off of the track.
Over here, we can see our current conceptual design, and it features the frontal scooper, the treads, and the perpendicular suspension system that we've already spoken about. It also features the collection bin above the clearance height required for our competition, and we would like to make the collection bin and the frontal scooper out of carbon fiber to reduce the weight of these components and to increase their durability.
So currently, in our design stage, we have finished our conceptual design, done our CAD drawings, and have started our simulations. We would like to be in our testing phase by next February. During this testing phase, the actual scooper and bucket will be made out of aluminum until we have begun manufacturing a carbon fiber. Carbon fiber is a long process, it takes a lot of molding and fabrication, so we'd like to be testing before we even start our manufacturing. Our next steps are to allocate a gearbox and find the correct springs for our suspension. Previous robots have had issues with the gearbox because there's a high torque on these treads. They've had issues with the drivetrain shearing, so we are currently selecting the correct gearbox for application. In addition, we need springs that are strong enough to take all the forces coming from the regular substance in addition to the 10 kilograms of weight. So currently we are running simulations to decide what our spring constants are going to be for our suspension.
Over here we have 2 of our simulations. The first one features the collection bin of a robot, and it's under a load of 10 kilograms, which is one of the requirements for a competition. That leaves the stresses in the structure that give a minimum factor of safety of 2, and this is the structure that will hold the frontal scooper. It's under a load of 3 kilograms, which leaves the stresses in a minimum factor of 9. These 2 safety factors are well above 1, which makes our concept design satisfactory for the competition. We would like to further develop these simulations so that we can know the exact size, location, and capacity of the actuators that will be connected to the ends of these structures. And we would also like to further develop our simulations for the suspension system coming up over the next month.
Finally, we have our programming, which needs to take into account the restricted bandwidth which we will be utilizing. We plan to handle that with packaged programs that will take every function and simplify it in terms of user control, reducing it down to hopefully 1-button operations. This is important because everything from the collection has a series of steps to it that's more complicated than just one action, because the collection happens where it digs into the ground at an angle, needs to set itself, and then travel forward, all to just gain the material into the excavator. And furthermore, we will have a simplified wiring layout, not to interfere with any other systems that are on board our robot's design. Thank you for your time. Questions?
Well, first of all, can you describe to us exactly what is it you have to do in this competition? And also, in quantitative terms, tell us what is it you have to do. Like, you have to go X number of meters with whatever.
The specified distance is not known to us in advance, but it is within these competition grounds. And from a starting location, we will be told to travel to some point in the competition grounds and then collect the material.
The robot starts in different positions on the field at any given time. We're not given exactly where it's going to be on the field. We're just told that it's on the field somewhere. We have to get the robot to go to where it needs to go, pick up the material, and then go dump it in the collection bin. We are able to have an autonomous mode, and we are able to have user input. However, in addition to the user input, we need to minimize the amount of bandwidth, so that if we are controlling the robot via remote control, we want to make it simple so that if we can push one button, it'll go collect, put it in its collection bin, then we can drive it over and dump it.
But even though you don't know the specifications, you must have an idea that you must be able to pick up something that's 20 pounds.
Oh, 10 kilograms. 10 kilograms is the
10
amount.
kilograms
Inside
is
the-
the minimum that we need to have inside our collection bin, and every kilogram above that awards us additional consideration. And we are aiming for additional weight, but as you said before, we have right now a factor of safety of 2 with 10 kilograms.
That means we have more room to play with, and that means the collection bin can hold more than 10, and the structure will still hold fine under the stresses.
What was your other question? I'm sorry, you asked for the specifications of the distance?
But I did say, in terms of quantitatively, you know?
Yeah.
Yes.
So minimum of 10 kilograms. And because we have factory safety issue, that's initially, we did that with the aluminum, correct? So yeah, we did that initially with aluminum. Carbon fiber is stronger than aluminum. So we actually have a higher factor of safety. We just haven't continued the simulations yet. However, hypothetically, it should be able to take more than 10 kilograms.
You're being funded by NASA?
No, we are currently being funded through FIU's Robotics Club.
Yeah, we have a couple of funding sources. We have the robotics club, and then our advisor, Tosunoglu, has aided us a little bit. He's given us a small sponsorship to aid us in funding of the robot. It's estimated the robot will be between $2,000 and $3,000. We also have a lot of components that have been donated from previous robots that are in the robotics club. There's about 80-something members in the robotics club, and there's a lot of stuff in that room that we're able to play with, which is very nice.
Explain to me why you need to use graphite composites for the collector tank and the bucket.
So
We don't need to per se, but given that
What's the benefit?
the
Does the benefit outweigh the expense when we go there?
Well, we'll like to reduce the weight as much as we can, because ultimately this is a competition that's meant to make a robot that theoretically would go to Mars. And every kilogram of weight that you have over, then it's more expensive for NASA to then take that.
Do you get more points if the robot
Yes,
is less?
weight consideration is one of the largest detractors of points in this competition, considerably more so than points per weight stored. So given that we lose 8 points for every bit of mass on the robot itself, and we can only gain 3 points for every bit of mass collected, it's a higher consideration that we have. So we're stressing it.
And is that your biggest source of weight, those two components?
Yes, they are our largest.
They're the largest components on the robot, and they are under the most amount of stress, as they will be digging into rocks, digging into substances. And previously, other robots have used aluminum. The aluminum tends to warp and bend. Sometimes it gets little pressure cracks and things like that. We want to avoid all of that. Although carbon fiber does take a lot of processing, we have the experience to do it. We also have sponsorship opportunities through the FSA team on campus that already has a carbon fiber sponsorship. We have most of the parts we need to work with the carbon fiber, including the vacuum bags, the vacuum pump, and a lot of these pieces that we need to process it. So the cost-benefit analysis, even though carbon fiber is expensive, I think for our experience in this actual design, our whole senior process, I think it would be beneficial to us to work with it.
Okay, talk to me about simulation with the carbon fiber, because it's anisotropic, so how are you modeling that?
The carbon fiber simulations have not been done yet. This is something that's coming up over the next month. So it's the first thing that we will begin to tackle for simulations will be carbon fiber. So I cannot have the details for that yet, but I can tell you that we're going to be working hard on it.
Okay. Mike?
Any comments? Thank you.
Thank you for your time.